174.8 kilometers per hour. It's the new world record on rails.
A jet takes off at 300 kilometers an hour. We're now doing almost twice that.
The quest for supertrains entered a new phase in the 1950s, when locomotives went from 140 kilometers per hour to the mad speed of 330 kilometers per hour, with equipment pushed to its limits and conductors facing unknown risks.
The design techniques of the time made it impossible to predict what would happen.
Thanks to 3D reconstructions, we will see the impact of innovative technology and construction secrets that enabled engineers to break records that were considered unattainable.
The TGV runs with a helicopter turbine.
We had to invent completely new tools.
From generation to generation, trains were going faster and faster. There were some foolhardy projects, yet also a revolutionary engine.
The aerotrain hovers thanks to its air cushion, so it almost completely eliminates friction.
From the first electric locomotives pushed to their limits, to AGV trains approaching 600 kilometers per hour, via the TGV and the aerotrain with its exceptional propulsion, this is the incredible story of the race for speed on rails. It all starts in the mid-1950s in post-war France.
The mood is optimistic and speed is all the rage.
And the speed of trains in particular. However, the steam locomotives of the 50s can't go beyond 140 kilometers per hour, since to reach this speed, the heat in the furnace must exceed 800 degrees Celsius, a temperature obtained thanks to the presence of multiple pipes in the water tank.
The more tubes there are, the more heating surface there is, so the more steam can be released.
1 litre of cold water produces 173 litres of steam. This vapour exerts pressure on a piston. The piston creates a back and forth movement on a connecting rod. The connecting rod attached to a wheel will make the engine go faster and faster.
Trains could now run up to 160 kilometers per hour.
Yet to exceed this speed, you have to rethink the train and forget about coal-fired engines. With this in mind, the French engineers are looking for inspiration from the Paris Metro and its electrical technology.
We immediately saw that electricity could produce much higher power at much lower costs.
In 1952, the SNCF, France's state-run railway, decides to electrify the track between Paris and Lyon. A power station will provide the energy the train needs. A 1,500 volt current is thus transmitted in a copper wire above the railway track, called a catenary.
The faster a train goes, the tighter the catenary must be to allow the train to draw sufficient electricity.
The rigidity of the copper wire is essential, since it has to withstand the pressure exerted by a key part of the train. It's the pantograph, a bow-like structure located on top of the lead car, which is responsible for collecting the electric current. The pantograph is a revolutionary invention. 70 years later, it is still present on the most recent high-speed trains. It still weighs as much as ever, nearly 200 kilograms. In the beginning, its details are a well-kept secret. Even today, several parts are still protected by patents, such as its rate of air resistance.
The pantograph is a bit like an airplane wing. It pushes upwards.
In spite of the pressure caused by the speed, the composition of the bow prevents it from being torn off. Its structure and attachments constitute an intricate piece of engineering. However, at this level of speed, there's a problem. By lifting the copper wire several centimeters, it would only take a few minutes for the bow to be cut in half under the effect of the speed. The engineers will have to find a solution.
The catenary was laid out in zigzag form so that it can glide across the pantograph. If the line was straight, it would have the effect of a saw, and then after 1 kilometer, your pantograph would be cut in two.
A bow is 70 or 65 centimeters wide. You have to use its whole length for the zigzag of the catenary, which may then glide sideways for several dozen centimeters.
Once the contact is made, the current is sent to a transformer and then to the motors on the bogies, huge carts with wheels. The electric current will thus directly feed the motors. It's a system that promises unprecedented power, enabling trains to reach levels of speed never before attained. 2 manufacturers are chosen for the job, Alstom and Schneider.
That meant 2 locomotives, each with a different technology.
The BB type and the CC.
Schneider's BB has 4 wheels per bogie. Alstom CC has 6, which gives it better grip at high speed. Both trains will be a complete innovation on the railway market and are intended to become showpieces of French engineering. However, there's no thought of chasing records yet. To inaugurate the new era on February 21st, 1954, the engineers will perform a test on the line between Paris and Lyon. The CC will go at full speed in order to observe its behavior.
The train, which was designed to run at 160 kilometers per hour, actually ran at 243 kilometers per hour.
243 kilometers per hour. It's a speed record. The success of this test with totally standard equipment will highly motivate the engineers. Now one of them, Fernand Nouvion, is proposing the greatest railway challenge of the time: to launch the 2 new trains at full speed while giving them a power never before developed.
The question was, where can we stage a test at such speeds? And as it happens, in the southwest, there's a line which runs perfectly straight for 40 kilometers.
Once the trajectory has been defined, some modifications are made to push the engines to the maximum of their possibilities. The conductivity of the catenary through which the current passes is increased to 2000 volts instead of the 1500, which are the norm on the railway network.
This way, the engines will develop powers of 8 megawatts, whereas they were designed for 3 or 4. That's more than double the design specifications.
Nobody knows yet what problems may occur beyond 250 kilometers per hour. However, the engineers are imaginative.
The windshields of the locomotives were fitted with wire mesh. There was a fear of bird strikes. At 300 kilometers per hour, this might cause severe damage to the driver's cabin.
With such high starting power, it was also feared that during the first few meters, it would be difficult for the conductor to control the power of the engines and prevent the wheels from slipping. So the manufacturers decided to create a special device to provide an anti-skid system.
That's why there's sand on board the engines, to increase grip.
The sand prevents slippage when starting up. It's still used on today's engines. They have tanks that open to pour out the necessary amount of sand. On March 28, 1955, the Alstom CC sets off on the 40 kilometers of straight line. An engine equipped with the latest technology. It's hoped that it will reach a speed of 300 kilometers per hour, or more if possible. Soon the CC reaches the record speed of the previous year, 243 kilometers per hour, and the locomotive is ready to go much faster. The symbolic barrier of 300 kilometers per hour has been reached. Yet at such a performance, the technology is being stretched to its limits. In particular, the catenary is showing worrying signs.
The contact wire and the pantograph went like this. Electricity arced in all directions. The bow began to melt, and as the pantograph was almost destroyed, they took emergency measures and lowered it.
The locomotive pulverizes 243 kilometers per hour. They had gone at over 300 kilometers per hour. Yet, the order is given to stop the train as soon as possible. The CC could have gone even faster, but it might also go off the rails at any moment. The men on board are in danger. A seemingly curious order is given to the engineers on the train.
They were told to open all windows to allow air to get in and to decelerate the whole thing. There was no question at the time of braking at 331 kilometers per hour. We just didn't know how to do it.
Today, engines allow for testing emergency stops at such speeds. The 390 tons of the latest trains will stop after 3,000 meters. The CC only stopped after 10,000 meters, and there was severe damage to the engine.
The CC had destroyed its transmission system and melted its pantograph. It had reached the limits of feasibility.
The CC had broken the speed record. Yet when it arrives at the platform, the feat is not made public. The top brass of the SNCF has issued a directive that the results shall not be communicated before the second day and the performance of Schneider's BB train. There's fear that one of the two engines will be significantly less efficient than its competitor. The financial stakes for both companies are colossal. State orders for new trains would ensure business for years. The next day, March 29, 1955, it's the turn of Schneider's BB to attempt the world record. After a few minutes, the train reaches a maximum speed of 331 kilometers per hour. On arrival, the results of the two tests are finally announced. Surprisingly, it's the same speed for the BB and the CC. It's a figure that satisfies everyone, but it's not true. The CC never reached 331 kilometers per hour, but stopped at 320. It could have gone faster, but for safety reasons, it was decided to make do with this speed. So the record, in fact, properly belongs to Schneider. What's more, the Schneider BB achieved this record with a handicap compared to the Alstom train. The day after the CC's performance, the temperature had risen considerably. On the day of the BB's run, it was much warmer.
A difference of almost 10 degrees Celsius causes a noticeable relaxation of the catenary.
A relaxed catenary poses the risk of considerable undulation when the pantograph exerts pressure from below.
And that hinders current collection.
Without these power cuts, the BB might have gone well beyond 331 kilometers per hour. Yet its performance close to the Alstom engine suits everyone. And the news of a world record set by two different engines resonates across borders.
It made news headlines, regional as well as national, and even in the international press. 331 kilometers per hour was the absolute world speed record for trains at the time.
The double feat set an example for all countries looking for solutions in future rail traffic. The manufacturers, Alstom and Schneider, would charge a high price for their know-how, as the world market for trains offered spectacular possibilities. But these exploits also whet the appetite of other companies. 2 years after the dual speed record, an engine straight out of the future sees the light of day. The ambition of its makers to shatter the state-financed record by surpassing 350 kilometers per hour. It's called the Aerotrain. This exceptional invention with its unique mechanics, which makes conventional trains look totally outdated, is the brainchild of Jean Bertin, an ingenious inventor in the field of aeronautics, a daring entrepreneur, and a major player in advanced post-war research. His latest project, the Aerotrain, is a kind of rocket propelled horizontally by a system quite different from trains.
To move at high speeds, the Aerotrain blows air under itself. It then lifts up by a few centimeters thanks to its air cushion and thus almost completely avoids friction.
It's a technology that is dispensed with the wheel. After thousands of years, it was a gigantic step.
The Aerotrain runs on an inverted T-shaped rail. A turbine drives fans that raise the whole configuration. The Aerotrain then rests on a real air cushion. A second helicopter turbine, positioned at the rear, drives a propeller of 2.4 meters in diameter, composed of 7 blades.
You just have to push, and on its cushion of air, it will move at an extraordinary speed.
There is still air resistance, but no more rolling resistance.
However, it takes another 10 years of studies before the ultimate prototype of the Aerotrain enters the race, demonstrating to the world that it's the future of high-speed transport. On January 22, 1969, Jean Bertin launches his horizontal rocket on its concrete rail. The peak speed obtained, as announced by the engineer, seemed incredible. 422 kilometers per hour, nearly 100 kilometers more than the 331 kilometers per hour of the previous record. While Jean Bertin continues to work on the prototype of his Aerotrain, the engineers of the classic railway are embarking on a new project. It has to be revolutionary as well, with a new design, a top speed never before reached, yet inspired by the Aerotrain in its motorization. The principle of the Aerotrain is adapted. The train will produce its own energy without the help of a catenary. Inside the engine, a gas-powered turbine will activate an alternator, which in turn will create electricity, which then will feed the motors in the bogies. This new system will allow trains to run even faster and to break the existing speed records. The TGV is born.
TGV simply means high-speed turbo train.
The challenge for the railway engineers is set: to demonstrate the level of technology achieved by surpassing the existing record with the highest speed ever attained. But to do so, they will have to transform the old trains that have served their purpose by new engines adapted to high speed. For the first time, a train isn't pulled by a locomotive, but made up of 2 motorized cars at each end that can run in either direction.
This is extremely important. A train that is reversible allows us to use it much better.
If trains go faster, traffic on the tracks will intensify. Therefore, it's necessary to be able to save time on shunting in stations. Thanks to the new design, trains can leave in both directions. And that's a definite plus compared to the Aerotrain, which can only run one way. The front and rear cars of the TGV also undergo an outward transformation, since new levels of speed open a new field of concern. It's aerodynamics, or in short, drag. How can the previous speed record be broken when the design of the classic locomotives acts like a brake? Air resistance is catastrophic. Their front is worse than the wall. As it repels the air, it slows down the train. The result is a waste of electrical energy.
Air resistance is a predominant factor in energy consumption.
Better aerodynamics would allow power consumption to be reduced by 20%.
The aim is to prevent the air from impacting the shape you have in mind as much as possible.
The best examples of the time are the designs of cars. Their bodywork takes on new aerodynamic shapes. That's why Alstom, the builder of the future TGV, is going to call on the man who designed the latest Porsches.
And that is Jacques Cooper.
Cooper is going to transform the shape of the train. The point of the leading car is considerably lengthened. It's a revolution in railways, but an outright necessity so as not to be slowed down by the air mass.
When we swim, we fight against a mass, and we make efforts to move forward against that mass. With air, it's exactly the same. As soon as you advance, you create turbulence, and the effect of that turbulence is that it holds the object back.
Yet if the air can be better pierced by the front end of the train, it can still get caught between the cars, as was the case with previous trains. So how do you improve a train to break a speed record? What transformations must be applied so that the train can penetrate the opaque mass of air? You just have to imagine another revolution. And this one will concern the bogies, those massive carriages comprising the axles and the wheels under the cars carrying the passengers. They are relocated to fit between the carriages and are hooked up by a cylinder. As a result, the train now looks like one long tube. The air no longer has any points of attack. And this design also offers a huge advantage from a safety point of view.
Experience has shown that when a train derails, the cars stay firmly attached to each other, and this solidity prevents it from settling down.
When the bogies were spread out under the trains, it was enough for the head end of the train to derail, so that the following cars would take completely random paths. With the bogies between the cars, the train becomes a single unit, and the chances of them going completely off the rails are almost nil. Fewer bogies in the train also mean that its overall weight can be reduced by several tens of tons. But if the TGV is going to break all speed records, the driver too needs extra help.
In high-speed trains, the driver no longer has time to see the signals, so we had to invent another system.
On TGVs, sensors are placed in front of the first axle and constantly read the speed at which the train is allowed to travel. On today's high-speed lines, it's still this procedure that enables the driver to keep the authorized speed.
We have a safety system to alert the driver when he's going too fast, and if it doesn't get a reaction, it automatically activates a device that will stop the train.
All these innovations are in place to ensure a smooth attempt at the world speed record. On December 8, 1972, TGV 001 sets off on the same track as the previous trains. In the train, a wagon is filled with high tech that analyzes its performance in real time. While the engineers scrutinize the data on the train's behavior, all eyes are glued on the speed dial. "318 kilometers per hour, a promising start." If the helicopter turbine can be developed just a little more, the engineers think that they will reach the 420 kilometers per hour of the aerotrain. Their company now has a potential riposte to the craze generated by Jean Bertin's engine. Alas, this is 1973, a year of worldwide repercussions which will condemn the future of the aerotrain and the TGV 001. The oil crisis causes a worldwide upheaval. The price for a barrel of crude explodes. And the helicopter turbines in the aerotrain and the TGV are big fuel consumers.
So, in the end, this technique was a failure.
The TGV project, as well as the aerotrain, are shelved.
It killed the aerotrain, it killed my father. He died a few months later.
Yet during all these years, the aerotrain had made the conventional railroad seem like a thing of the past. And now there's another means of electric transport. It's the Shinkansen, the new star of Japan's railways. Running at a commercial speed that's remarkable at the time, 210 kilometers per hour. But the Shinkansen is not comparable to the French trains because it's a shuttle with magnetic levitation. The cars lift thanks to powerful magnets. However, this vision of modern transport adds to the image of the train as being hopelessly outmoded.
A minister at the time said, "The train is finished."
But the French engineers are determined to take up the challenge and to strike a big blow to reverse the trend.
A lot of engineers went to see what was being done in Japan with the Shinkansen system, and that helped a lot to broaden views.
Since on December 21st, 1971, the Japanese train reaches 517 kilometers per hour, an incredible speed. Yet it's achieved on a special monorail track, while in France, tracks have to accommodate freight trains, and there are even still sections for classic trains. It's evident, however, that the race for speed is now run on a worldwide scale, and so new technologies are called for. To compete in the race, it takes nothing less than a brand new train. However, it must comply with two requirements. It has to be 100% electric, so that it doesn't depend on rising oil prices, and it must be able to run at very high speeds every day. Yet the engineers don't have to look far to find the answer. All it needs is the TGV with a new formula, without its helicopter turbine and re-equipped with a pantograph. In other words, a TGV 2.0. It's the one we know today, a train imagined almost 50 years ago. Yet to run it at 250 kilometers per hour every day, there is an obligation.
There has to be a difference of 150 to 200 kilometers per hour between the record speed of trains and the commercial speed.
If you want a train that runs comfortably at 260 kilometers per hour and well within safety margins, you have to prove that the train can go over 380 kilometers per hour without any problems. The margin is required to reassure not only the officials, but also future passengers. So once again, the race is on. The bar is set at 100 meters per second. The project is christened TGV 100. To prepare for the new speed record, not only will the train be profoundly modified, but the track too. Since the electric current coming from the power stations is going to jump from the traditional 1,500 to 25,000 volts. To guarantee such a powerful electric current all along the line, you have to build substations at a distance of 50 kilometers. These small bases will adapt and reduce the gross power sent by the central station. For the high-speed line between Paris and Lyon, control and management of the substations is done from Paris. Here they check that the intensity of the power supply from the small copper wire is constant. The catenary receives a current 20 times more powerful than before. But it also must be adapted to the specific conditions of a record run, because the engineers anticipate a problem. The pantograph, by pressing on the catenary at high speeds, will create a ripple in the copper wire. It's a phenomenon dreaded by engineers. If the pantograph catches up with the undulation, it will lose contact with the copper wire and only hit it intermittently.
If you tear off the catenary, it means disaster.
So how do you make the catenary lift as little as possible and stay in constant contact with the pantograph?
On a high-speed line, the catenary is stretched to 2,600 decanewton. That's almost twice the tension on a conventional line.
The counterweights on the masts are increased to further stiffen the structure that holds the catenary, an indispensable process. The infrastructure on the ground is modified too, since the old 30-meter rails cause a shock each time the train passes over a weld. The whole system is therefore redesigned.
We now manufacture rails that are almost 300 meters long and are delivered by special trains.
These bars are assembled using a special technique. They're welded with aluminium.
The result is a rail without any intermediate mechanical joint.
The disadvantage of extremely long rails is that when temperatures rise, they tend to bend upwards along their entire length.
So we chose very heavy rails, weighing 60 kilograms per meter, so they won't lift.
With a target speed of 380 kilometers per hour, the infrastructure around the train has been rethought to correspond to the laws of physics. Yet no rail-bound train has ever approached the speed of the record envisaged. It's a leap into the unknown. The whole country has its eyes riveted on the record attempt. It's like launching a rocket in the horizontal. The tension mounts. In the car behind the driver, there are engineers to observe and retrieve the information provided by the train itself.
Of course, the train was loaded with sensors, as during all the previous runs.
On February 26, 1981, the TGV 100 gets rolling. For conductor Jacques Ruisse, going for the 380 kilometers per hour is beyond anything he's done before.
In the cabin, you have a threshold at 170 where you can see the train's accelerating. Then you have another one at 210 and again at 280.
However, Jacques Ruisse is not alone. Engineers and managers are present to assist the driver.
On the photos, they tell me I look tense. But when you're going that fast, you can't let yourself be distracted by people in the cabin.
120 seconds. 372 kilometers per hour. 73, 74, 75, 76, 77, 78, 79, 80. We've reached 380 kilometers per hour.
380 kilometers per hour. The world record of 1955 is beaten, but they can't go any faster. Due to the force of the airstream, the pantograph lifts off dangerously from the train, pushing the catenary much too high.
We already had a lift of more than 21 centimeters, so we stopped at 380.
The limits of the TGV 100 have been reached. Yet the performance is unprecedented, with a train and installations that will be used in everyday traffic. It's state-of-the-art technology at the service of passengers. This train is not a utopia, it's the very train that will race into the future.
The interesting aspect was that we were breaking records with commercial equipment.
The world record makes the TGV a worldwide success, and the lines spread all over France. The high-speed train becomes the new icon of the railway. Passengers are eager to board the orange train. But like all records, this one too will be hunted down. 7 years later, on May 1st, 1988, the German manufacturer Siemens sends its ICE between Hanover and Würzburg at 406 kilometers per hour. France loses its title. It's a blow to the nation's pride. At the manufacturer Alstom, there is only one goal now, that of overtaking the Germans. All forces are going to focus on this objective. The commercial future of one of the jewels of French technology is at stake. They must strike hard this time, so as not to be overtaken again a few months later. The aim is to crush any hopes of being on an equal footing with the French railway industry. The envisaged speed must kill off all competition for a long time to come.
We were hoping to break the 500 mark.
500 kilometers an hour, a mythical barrier. Yet how are the engineers going to achieve this feat? Will they be able to improve the rigidity of the catenary so that it won't be torn at over 380 kilometers per hour? And what are the new constraints at that speed?
At 600 kilometers per hour, an Airbus is well into the air.
Again, they have to push the limits of the train and work on its body of steel. Since during the previous record, at 380 kilometers per hour, the sides of the train began to erode.
The bay windows protruded slightly from the sheet metal, so the higher the speed, the more they were exposed to the air rush. And we're talking about sheet metal just a few millimeters thick.
With an imperfect airflow, everything that protrudes is gnawed away.
So when the train's underway, there's a continuous abrasion of 3 to 4 hours.
The effect is a real break on the train, so the fuselage has to be perfected down to the last millimeter. For the first time, rubber membranes are placed between the cars. The designers work on the aerodynamics of the first car, but also on the tail end of the train, so that the air will flow without too much rupture. Metal shields are placed on the bogies to prevent the air from getting inside. The diameter of the wheels, which is traditionally 920 millimeters, is increased to gain speed. On top of the train, the pantograph is put on a firmer suspension so as not to lift the catenary, as happened during the 1981 record, when the copper wire had been pushed up about 20 centimeters. It's tightened once again to ensure the closest possible contact with the bow. But it's not only the train that is modified. The infrastructure is also adapted. The line is secured by 2 to 3 meter high fences all along its length to prevent accidents involving animals crossing the tracks.
Game struck by a TGV at 300 kilometers per hour causes a lot of damage.
But fences may not be enough. There's also surveillance along the tracks.
There are some hunters and hunting federations with whom we have partnerships, who will hunt game along the line or try to scare it away.
Everything's ready for the record. But before they invite the press from all over the world, a number of high-speed tests will be performed. Several times the train approaches the 500 mark.
We were gradually increasing the speed, and each time we'd monitor all the data to check that we were still within a safe margin. Then, on May 18th, 1990, we told the top brass, "Okay, we can go."
The public holds its breath as the record attempt is covered live on television. Are the engineers going to win their bet and exceed 500 kilometers per hour on rails? Nobody has ever done it. Suspense is total.
Speed 494. Passing Vendôme Station in a few seconds. Passing Vendôme Station. Speed 495.17.
Just a few kilometers per hour away from the magic 500. Yet anything can still happen. The catenary may rip. The pantograph may be torn away by the speed. The engineers on board scrutinize the reactions recorded by the sensors. Anxiety and excitement become one until the delivery.
500. 514, 15, 515 point something. I'll read out later. Cut all tractions. We're watching. It's not over yet.
After being held for 2 years by the Germans, France recovers the rail speed record on May 18, 1990. The German interlude apart, France has held the world record for the past 36 years. the TGV brand has re-established itself and is exported all over the world. 16 years will pass until in 2006, the railway engineers roll up their sleeves once again. France's State Railway is preparing the opening of a new line between Paris and Strasbourg. A new speed record on this track will give it an exceptional boost. The new track offers 200 kilometers at high speed, with a straight section of more than 40 kilometers and bends with comfortably large radii. The V150 project for 150 meters per second has been born. And again, there'll be a new version of the TGV, a real super train. It's the AGV, the Alstom high-speed train with new motorization.
A rotor that rotates inside the engine and drives the wheels.
The AGV engine weighs 3/4 of a ton and consists of two parts. There's a stator made of sheet metal, inside of which a motor winding receives the electric current. In its center, there is a rotor made of an assembly of sheet metal and cobalt magnets, providing a magnetic force of exceptional dimensions. The stator turns the rotor. The power thus generated is phenomenal for a motor classified as light. But there's another special feature. There isn't only a motor at the head and the tail of the train. There's also one on each of the bogies between the cars. But this creates its own problems.
All metal tools were banned from the production lines because the tiniest key or any hammer would immediately stick to the magnets. The technicians had enormous difficulties mounting these motors.
The power of the engines is considerable. Theoretically, the train can approach 600 kilometers per hour. Its 8 engines are equivalent to 8,000 cars. As for the outward design, the AGV is given an even more rounded shape.
We were approaching the sphere of aviation technology.
Yet at more than 500 kilometers per hour, there are new problems, like strong crosswinds. They can tip up to 80% of the weight of the train to one side.
Crosswinds meeting too square a shape, even if it's tapered, will tend to cause much more lift, so that's why we rounded the corners even more.
At the front, the windshield also becomes flush for better penetration of the air. And in the bodywork, the engineers have hidden over 600 sensors to record the train's behavior. There are even miniature recorders on the wheels. During the first tests, the train goes over 500 kilometers per hour. But then, the hubcaps covering the sensors give way. At this speed, they're simply torn off by the airstream. So the manufacturer decides to put thicker covers on the sensors. Yet it's the covers that cause a real panic during a test run. 5 days prior to the date set for the record attempt, on March 29, 2007, the press is invited aboard the AGV to spread word on the comfort of travelling at 500 kilometers per hour.
When we reached 506 kilometers per hour, we heard a phenomenal noise, which of course scared everyone.
It's caused by one of the hubcaps that came off the wheel.
People were clinging to their seats, thinking, "My God, what's happening?"
The train performs an emergency stop. And this time, it takes a mere 3 kilometers to stop, instead of 10. It's a new record, but one that was never meant to be set. For the first time in history, a train has made a stop at more than 500 kilometers per hour. But it proves that the train can cope with the most unexpected situations. In less than 3 months, 40 tests are carried out, gradually increasing the speed. On April 2, 2007, the train even reaches 568 kilometers per hour, an incredible speed that takes everyone by surprise. Nobody imagined that the train might go that fast during the tests. even the plane chartered to take pictures was not fast enough to keep up with the train.
The plane had to fly at low altitude, so its speed was limited. And in this case, the train was going faster than the plane.
All the indicators give the green light. The next day, the French and the international media follow the world speed record attempt live on TV. Will the train exceed the 515 kilometers per hour of the 1990 record?
Messieurs, c'est parti.
It's 1 p.m. The train leaves from the town of Prony in the direction of Nancy, Paris. After 10 kilometers, the AGV begins to accelerate in earnest, fed by the electrical voltage sent to the catenary from this point onwards.
The normal voltage of 25,000 volts had been increased to 31,000 volts to provide additional power.
6,000 volts more. That's a 25% rise in the power sent to the copper wire.
There we go.
Initial voltage 31.2 kV.
Go to 360.
360.
Correct.
710A, 29.9 kV.
The rigidity of the catenary brought about by the counterweights on the masts has been increased by 50% to withstand the wave generated by the bow.
You can't jump from 2 tons to 4 tons, that would be too abrupt. We stretch to 2.8 tons, then to 3 tons, so that we have progressive tension and approach the record zone with a tension of 4 tons.
The train is at full power, but if the speed is too high, the train will derail.
There was a succession of curves with ever larger radii. In the first curve, we could run at 350 kilometers an hour. We'd seen that up to 350 all would go well, but at 355, the train would lean over sideways and derail.
It takes Eric Pichak just 10 minutes to reach the speed of the previous record from 1990. 515.3 kilometers per hour. And the speed is getting higher and higher. 13 minutes. 574.8 kilometers per hour, or almost 160 meters per second.
Attention all, after control and validation, the official speed reached during our run is 574.8 kilometers per hour.
17 years after the 1990 exploits, the third-generation TGV exceeds the previous record by 59 kilometers per hour. It's almost half the speed of sound. The commercial speed with passengers can therefore be pushed to 320 kilometers per hour on a daily basis.
Today we're driving at speeds that were world records not so long ago.
Exceeding 574 kilometers per hour has become the yardstick for any country when attempting a record. Japan has achieved this by driving at over 600 kilometers per hour. However, on rails that can only support the Shinkansen. Yet, there are other nations ready to enter the race.
The Chinese would love to take this record away from us. Let's wait and see.
The Americans and their brilliant inventor Elon Musk are working on it with an incredible concept, the Hyperloop. The passengers will sit in a capsule and the cylindrical train will move in a long vacuum tube. Thanks to a levitation system created by powerful magnets, the capsule will be hovering without friction and without air resistance, so that nothing can hinder the shuttle's progress. With a powerful electric motor, it could reach speeds unimaginable a few years ago and exceed 1,000 kilometers per hour. But this is still only a concept, and it has met with considerable skepticism.
Maybe I'm a bit harsh, but for me it's a PR stunt. How can you drive a vehicle at an extremely high speed in a vacuum tube without running into a great number of problems? Then there's the psychological side. Imagine a passenger locked up in a vacuum tube for 10, 20, 30 minutes on end.
The other problem, one already encountered by Jean Bertin's Aerotrain, is the prohibitive cost of the infrastructure for the Hyperloop.
Like the Aerotrain, these systems require that whole urban areas be flattened to allow them access to city centres, whereas the TGV is able to run on tracks that have been around for 2 centuries.
A new speed record reaching 650 or 700 kilometers per hour would mean that commercial trains could run at 380 or even 400 kilometers per hour. Yet at this level, the budget would explode.
The faster we go, the more expensive it gets to manufacture and maintain the cars.
Costs for going from 320 to 380 kilometers per hour would quadruple. For the time being, the race for speed is taking a break. It will be many years before engineers will work on a new record. These days, ecological aspects call for moderation, and demand is focused on passenger comfort. From the first locomotives running on electricity, like the CC 7100, to the latest double-decker TGV trains, and the incredible Aerotrain. The race for speed on rails has helped to develop a know-how that is unique and is exported all over the world. The TGV 4.0, planned for the next decade, will be a synthesis of all the technological innovations implemented over the past 50 years. Comfort of transport, silent running within the cars, a low carbon footprint, 5G connectivity, everything is combined to make this train the new state-of-the-art reference for rail travel. The Japanese, with their maglev rocket, exceeded 603 kilometers per hour for about 10 seconds. A new world record for a levitating train, thanks to powerful magnets. The TGV still holds the record for a train that can run on rails, which are decades old. Yet, there's the vision of cracking the 700 mark. And history has shown that sometimes, even the most incredible goals can be reached.